Welcome back. Now we're going to talk about second order or second derivatives for partial derivatives. So given a function f of xy, we could find a second derivative, and that could be noted in this manner. So this essentially means we're taking the partial with respect to x twice. So another notation for this would be second partial of f with respect to y, or f of y. So you differentiate with respect to y both times. All right, now that's not the only way we could do it. I could have second partial with respect to f, and then I could have partial x, partial y, or f yx. Lastly, I could write this one third way. Second partial with respect to x, I could have partial y, partial x, or fxy. All right, so it depends on how the equation is defined. One way you could think about breaking this down, that could be like the derivative with respect to y of the derivative of the function with respect to x. So we would have to take the derivative with respect to x first and then apply that y to it. Second, first, and then second. So if I write this out, if I have d2f dx dy, I'm actually going to throw some color in there. We'll say dx dy. That means differentiate first with respect to y, and second with respect to x. So that's what this notation means. Up here, this is first with respect to x and then with respect to y. So think about like an inside-outside situation, or we could say partial y with respect to x. So here's another notation. And this would say differentiate first with respect to y, right? That y is on the inside. We deal with that first, and then we apply that outside x. Oops, I'm just jumbling that together. So first with respect to y, then with respect to x. So the other way this might be written would be f of yx. So we apply y first, then we apply that x. All right, all three of those mean the same thing. All right, let's do an example. In this example, we're given a function of two variables, x times cosine y plus y times e to the x. And we are asked to find four different second derivatives. So in order to find the second derivatives, we need the first derivatives. So the first thing I'm going to do is find each of those. So A, partial f, partial x. So that means treat y as a constant. So cosine y, that's a constant. I'll just get cosine y, that coefficient of x. Y is a constant. The derivative of e to the x is e to the x, so I'll just have plus y e to the x. And partial of f with respect to y. That means treat x as a constant. X is a constant. And since it's a constant, it's like a coefficient in front of cosine y. The derivative of cosine is negative sine. So I have negative x sine y. Again, x is a constant, so e to a constant, that's a constant, and that's a coefficient in front of y. So the derivative of, some coefficient times y is just going to be that coefficient, e to the x. So those are both of my first derivatives. So now I need to differentiate this with respect to x, and I need to differentiate with respect to y. Same for the second one. Differentiate with respect to y will give me this, and then differentiate with respect to x will give me that second one. So for B, the first thing I'm going to do is I'm going to differentiate with respect to x df dx. And so what that gives me is d2f over partial x squared. Right, so that's what I'll be finding. If I differentiate this Brown function with respect to x, that means treat y like a constant. So if y is a constant, cosine of y is a constant, the derivative of a constant is 0. So equals 0 plus y e to the x. E to the x is what we're differentiating with respect to. This is like a constant coefficient. So we will just get y e to the x. That's my answer. I should write it like this for that. Okay, so same thing here. I'm going to differentiate with respect to y. This Brown function we have df dx. So that gives me partial squared f partial y partial x. So I'm going to differentiate this guy, treating x as a constant. So the derivative of cosine y, that is negative sine y. Treating x as a constant, this is a coefficient. That y is going to go away, so I've got plus e to the x. So now we have to find the second y of y. So second partial of y, and that will be of df dy. So that's going to give me partial squared f over partial y squared. So that means treat x as a constant. If x is a constant, it's a coefficient. The derivative of sine is just going to be cosine y. So I have negative x cosine y. X is a constant, e to the x is a constant, and the derivative of a constant is 0. So my last piece here, I'm going to find the partial of x of the partial of f with respect to y. So that would give me partial squared f over partial x partial y. That means I'm treating y as a constant. X is my variable. So if y is a constant, sine of y is a constant. So negative sine y is the coefficient on x. Differentiating that, we're just going to get negative sine y. E to the x, the derivative of e to the x would be e to the x. And so there are my 4 different second derivatives. All right, so I want you to notice that partial y, partial x, and partial x, partial y, those are the same, right? They're the same second derivative. And that's not a coincidence. We actually have a theorem called the mixed derivative theorem, or rather Clairauts theorem. So I'm going to pull that in on the next page, and we're going to talk about that and then do one more example. So here we have the mixed derivative theorem, or Clairauts theorem. And so what we have here is if we have a multivariable function and all these partial derivatives are defined on an open region, on an interval, well, we don't say an interval because an interval would be on a line, so on an open region containing some point, if all of the derivatives are continuous at that point, then both of these second partial mixed derivatives are going to be equal. So for this example here, we are given a function w in terms of x and y, and we're asked to find the second partial mixed derivative. So that's the partial of w, first with respect to y, and then with respect to x. Now, if I try to take the derivative with respect to y first, that means x is a constant. So this first term, that would be easy. That would just turn into x. But this second term, I'd have to use the quotient rule. So by Clairauts theorem, we know that d2w, second partial w, partial y, partial x, that this, reversing that order, these guys are still the same. So that's what I'm going to do first. I'm first going to differentiate with respect to x and then with respect to y. So differentiating that function, w equals xy plus e to the y over, so y squared plus 1, I'm going to end up with partial w with respect to x equals, so respect to x, y is constant, so the derivative of yx is y. And then again, treating y as a constant, e to the y constant divided by y squared constant plus 1 constant, constant over constant. This is just one big constant, and the derivative of a constant is 0. So that's the partial of w with respect to x. So we get just y. So now, if I take that and I differentiate with respect to y, this function dw dx equals y, we go that one step further, I get d squared w, partial y, partial x. So differentiating y with respect to y gives us 1. So as you can see, this was clearly a much shorter way to go about this. And I know I said this would be my last example, but I tricked you guys. I just wanted you to hang out a little longer. I got one more because I just want to talk about a higher order derivative. So like a third or a fourth derivative. So higher order derivatives. Find partial z, y, x, y. Now, does the order matter? No, we know the order doesn't matter. We just need to use z once, x once, and y twice. So as we list our steps out, I mean, the order which we write these matters, but we know as long as I have 2 y's, an x, and a z in my final answer, it will be equal. So we have to look at our function, f of x, y, z is 1 minus 2 times x times y squared times z plus x squared times y. We need to think about what is going to be, or which variable is going to be best to differentiate with respect to first. So I'm going to choose y. The derivative of 1 is a constant, so that's 0, it's gone. So here I have y squared. Z and x would be constants if we are differentiating with respect to y squared. So I have 2xz y squared. The derivative of y squared is 2y. So I have 2xz, 2y, or 4xz y. Now, there was a negative in front of that, and I'm just going to rewrite that. So that's negative 4xyz. Differentiating this third term with respect to y, that means x squared is a coefficient, and I'm left with x squared. So now I'm going to take this function. I already differentiated partially with respect to y, and now I'm going to do partial derivative with respect to x. So that means x is a variable, y and z are constants, they're coefficients with that negative 4, and I have negative 4yz. Differentiating x squared partially with respect to x is going to give me 2x. All right, so now I'm going to take this partial derivative, first y, then x, and I'm going to apply y again. So differentiate with respect to y, z is a coefficient, so I've got minus 4z. X would be constant, so 2x is constant, and the derivative of a constant is 0. So for my last step here, I have f, I did y, then x, then y. What do I still need? Z. So the partial derivative of negative 4z with respect to z is negative 4. So that's my final answer. The order in which I added these could have been any order as long as they were all in there at the end. So these intermediate partials, they might be a little bit different depending on the order in which you apply them, but it's easiest to kind of look at these high powers and which variables we have more of first to help us think about breaking it down into smaller pieces to make it easier for us. So that wasn't the only set of 4 steps that I could have done to get that. All right, so we're done with partial derivatives. Hopefully you guys have a good feel of how to do them. And I had to pause and edit myself a whole lot in that video, so I hope that does not convey when you are watching it. All right, so stay safe out there. Have fun. Be good. You're on your own. Peace.